Hello friends, as you know, Bureau of Indian Standards has recently issued revisions of IS-1893. Part 1 and Part 5 have been released last month. And the buzz around these codes, these revisions, is that for the first time, uh, the hazard, earthquake hazard, has been characterized in probabilistic terms. And that is mostly put forward as the USP of this revision. I wonder how many of these people who are talking about this PSHA basis of hazard characterization really understand about the probabilistic methods as such. I put forward my views on this issue, and as you will notice that these are contrarian views with the aim to encourage discussion and debate to decide uh, the is it really the way we wish to take forward. So let's start. First of all, I delivered this talk in the at the invitation of Indian Concrete Institute and ISET local chapter Pune on 29th November. Somehow that recording, there was some technical glitch with the recording there. So I am recording this uh, video in my office in the Department of Earthquake Engineering, IIT Roorkee. But the content is more or less same. The discussions were much more engaging. Of course, that part is lost out, but hopefully, uh, I will be happy to engage with anybody, anyone who has any questions or clarification or anything to discuss that we talk about in this during this session. And this is going to be a little longish post, considering that I need to cover a lot of background and also discuss about the issues. So kindly bear with me. Some of the things may appear very elementary, for example, the response spectrum and the dynamic response issues, but I still need to cover that so that the issues of dynamic response to earthquake excitation is understood and while we discuss the hazard characterization. Okay, so let's start. So the structural design, the codification of design process essentially uh, is required. Every society has certain set of standards that is actually based on providing certain minimum assured safety to the dwellings, right? And essentially, the design codes represent the minimum requirements. That minimum is the keyword. Design codes represent the minimum requirements to ensure acceptable safety margin of the most common form of structure at the minimum cost. This is also important at the minimum cost. So minimum force requirements to ensure acceptable safety margin at the minimum cost. Right. So, what are the considerations for determining this acceptable safety? Right. So, this acceptable safety is a very, very fluid term. I mean, how do we understand what is acceptable safety? So, it has come from the historical context. Every society has some inherent implicit safety notion of safety built into their normal behavior. So the societal acceptance of inherent safety margin is implied in the design codes in use. Whatever design codes are in use now, they imply the safety margin that is accepted by the society. Now, the design codes may be required, revision may be required on account of developments in the technology, development in know-how, or even better material and to account for new processes, etc. But such a revision in code should not lead to any increase in design forces, that is, increase in safety margin, unless there is an evidence of inadequate safety margin in the existing code. So unless there has been some kind of catastrophic engineering failure, there is really no need to increase the force levels unnecessarily, right? Because that's a major issue with societal safety considerations. So how this structural design as a concept has evolved? As we know, need of shelter is as old as the civilization from the cavemen and all. So in ancient times, the shelters were built by trial and error, and these experiences by the practitioners of the craft evolved into several rules of thumb, often based on geometric proportion, and we still use some of these rules of thumbs even today. For example, the design of concrete gravity dams or gravity dams is still based on that middle third rule. The resultant should not pass beyond the middle third portion of the base, right? That is the no tension design rule. So such rules of thumbs have evolved over a period of time, and these rules of thumbs have been codified in the form of structural design codes based on different formats. So with the advancement in science and theoretical basis, these rules of thumbs were developed and formal codification took place, and that led to different design formats. For example, starting with permissible stress or working stress, then ultimate load, and the present method of limit state design. So the design, I mean, that is the code, but all our design processes actually involve analysis of the problem, and there are three analyses that we need to look at. First is the analysis of the load. What is the load that we need to apply? Characterization of the load. So that also needs to be studied. Analysis of response of structures to these applied loads. And then the analysis of safety of structures, the safety margin. How do we evaluate the margin of safety? Right? So unfortunately, the first and third analysis is rarely addressed in our curriculum. Most of the attention of structural engineering is devoted just to the analysis of structures to the applied loads. The analysis of loads itself requires a very rigorous surveys and a very serious, very time consuming, very tedious study to characterize the load. But we just borrow some numbers that is accepted. And accordingly, when these we are not very sure about the loads that we are dealing with, and we are not very sure of the safety margin of the structure available with us, there is really very little to be finicky about how accurate the response computation is going to be or should be. So it is of really no use to have extraordinarily high precision in the analysis of response if the loads and safety parameters themselves are not very well defined. So please keep this broad framework of the state of the art in practice of structural engineering while we go along. So the legal implications, codes are legal documents, and they are legally and ethically considered to be the minimum criteria that must be met by the design and construction community. If the owner wants to increase the safety margin, he is very well within his rights to consider higher magnitude of forces and be more safe. But code themselves should provide the minimum that society cannot go below this. And the basis of this building code development is to safeguard the health, safety, and welfare of the public. The first and foremost goal of building codes is the protection of human life from the failure of building life safety provisions or from structural collapse. So that is the main adherence, the main guiding principle that uh, life safety, the human life, should not be lost. And there are two basic formats. I mean, there are prescriptive codes that specify provisions to be incorporated to address certain specific issues. One example is our ductility details 13920 that just mentions that uh, the reinforcement has to be uh, particularly arranged in this form, the spacing between the ties and the distance, how long the length of the, how long that spacing, close spaced ties should be there in the beams and columns and so on. And it is assumed, it is just assumed that by doing this, somehow we will be achieving ductility of maybe around 5 or so. The global ductility at the structural level. Nobody knows, it's just assumption. And that is what we mean by prescriptive code. So code has just prescribed uh, some way of providing the ties and reinforcement details and just have to adhere to those, and the ductile behavior will be deemed to have been achieved. Right? There is no calculation, there is no rigid mathematical formulation for this to determine what ductility is actually achieved. And then there are other more general, more open-ended codes which define the problem and then define the broad framework, and then designers are allowed to devise their solution as long as they meet the criteria, that is constraints that are specified. So that is performance based performance codes. So now how do we go about? So safety margin, we talked about the society acceptance of safety. So and socio-economic conditions. So let us look at this map, global socio-economic variability. So where are we? India. This is the 2019 report by World Health Organization. This is the per capita healthcare spending by different countries. In India, we are second from the bottom here, right? So that is our healthcare spending. So it is a combination of several factors. Our cost of living, low cost of living, as we all know, that is reflected in this per capita healthcare spending in US dollar terms, right? So our healthcare itself, quality of healthcare is not necessarily very bad, and quality of healthcare of the highest spending countries like USA or the Great Britain, United Kingdom is not necessarily the best. But then the cost of living at these locations is so high that even to achieve the minimal care, the per capita expenditure in real terms, absolute terms, is very high. So this figure actually explains the uh, cost of living and the expense part. I mean, how affordable everything is in different countries. So that is a picture. I mean, this is how this picture should be looked at. Now we come to the risk behavior, global risk behavior. So global risk behavior, again, from the same World Health Organization report. So this is the road fatality accident. So road fatality per million vehicles per year versus the GDP per capita. This is 2018 data in thousands of US dollar terms. So, if you look at it, and this is the indication of what is the risk accepted by the society as a whole. Because if this is the accident rate, fatality rate, and even with this knowledge, if I am stepping out on the road, then I am willingly accepting this risk. And therefore, I mean, please pay attention to this thing. The United States per capita GDP per capita is about 90,000 US dollar. Right? It is somewhere here. So maybe 2018 or 17 data. So this point is probably United States or so. I don't know. Maybe. Current GDP per capita of India is less than 3,000 US dollars. So maybe somewhere here. So just imagine the risk acceptance, a perception towards the acceptable risk in our society, low GDP per capita society, and high GDP per capita society. And this is visible. And of course, just because we are accepting higher level of risk, that is why the cost of living is low. You may notice that it is a very common sight for tractor trolleys to be plying on highways. Tractor trolleys are not allowed on highways. They are not transport vehicles. They are farm equipment. Legally, they should not be on highways. And they have led to several accidents. We have lost one of our colleagues on the road from Roorkee to Delhi when the bricks loaded on the trolley, the tractor stopped in between, suddenly applied brakes, the bricks actually flew and completely the colleague who was in a taxi behind that tractor trolley was completely buried in the pile of bricks and he died after spending some time in coma. So that's the risk that we accept. So is this risk anyway comparable to the risk here? No, definitely not. Right? And again, please keep these differences in mind. We are operating at this level. And this risk is acceptable because it's a very common sight. Transportation of reinforcing large reinforcing bars or structural sections protruding out of the truck or whatever carrier vehicle they are being transported. It is not allowed. I mean, they happily move along in the highway with one red flag at the back, and that is obviously a serious threat, serious safety issue. But again, all goes. So that's our acceptance of the risk. And by accepting this high risk, we reduce the cost of living, which is reflected in this our per capita health expenditure. Everything is cheaper. If we accept more risk, everything is cheaper. I mean, even we can get prescription drugs over the counter without giving any prescription to the pharmacist. Very common practice. So that's the. I just want you to appreciate this fine point. What is the acceptance of the risk in our society, Indian society? So now we come to the design problem. As I said, the problem is to provide a safe shelter at minimum cost to the owner. The notion of safety is, first of all, the strength criteria. factored resistance should be greater than factored load. Right? So that is the basic limit state uh, design. And then again, after we satisfy the strength criteria, we apply this service check condition that the deflection or the drifts or whatever deformation, they should be less than the allowable deformations. And the cost, total cost of the facility or the building is actually comprises of three components. One is the capital expenditure, the offhand first time when we construct the facility, so that is the capital expenditures, C capex. Then there is a maintenance cost, which is the repair and maintenance over a period of time over its design life. And then third is the cost associated with loss. If something happens to the facility, it goes out of function, then what are the economic losses? What is if something happens and then some compensation has to be paid? So that is also an economic loss. So that is an economic loss. Right. So these all three components, they are again based on the socio-economic conditions of every society. Our cost of living is low, so the maintenance costs are going to be low. Economic losses are also going to be low, and capital expenditure maybe because everything costs less, so this capital expenditure is also low comparatively with respect to the other developed economies. So, and obviously the ratio, the proportion contribution of these is of course varies with society to society. Right? So these components are strongly coupled with the socio-economic factors of a community. So high safety and low cost are in general conflicting requirements, and a judicious trade-off is desired, and that is aimed at in design goals. Now, designing for higher intensities, I choose the force level for design very high. That will increase the initial capital cost, but because more material goes into the system construction, so maybe it will reduce the repair and maintenance cost and also the economic loss due to possible downtime. And if I reduce the design load, it may reduce the capital expenditure and maybe some possibility of increasing the maintenance cost and also the uh, economic loss in case of downtime. So there is a trade-off, and that depends on eventual condition and how this has to be looked at. So this again, this has to come from analysis of loads. How do I combine? How do I choose a load parameter, the load for design, considering all these factors, socio-economic factors, such that I come with the design gives me minimum total cost of ownership. Right? So that is how the various load combination factors that you find in the design code, they actually come from this particular consideration. Now, a lot has been made about the vision being first step towards performance-based design. So I need to put this in context. Performance-based design, as far as earthquake resistant design goes, is essentially specifying extent of damage because earthquakes are of different shapes and sizes. So it is not possible to expect the same performance against all possible earthquakes. It is not economical. It does not make sense. So the idea is we can specify different performance levels in the form of acceptable damage. So very frequent earthquake, no damage. Uh, Moderate earthquake, some partial damage, very large earthquake, rare earthquake, significant damage but no collapse, so on. And as the facility increases, it becomes more and more critical. We make more tighter specification towards the performance in terms of damage control, controlling the damage, or in a sense, essentially, damage is defined by the drift, lateral drift. So drift control mechanism. So what should be the drift measure for different intensities of earthquakes? So this is what performance-based design should aim for. What we are doing is this. We increase as the performance, the importance or critical or facilities importance is increased. So we just design it because our basic design principle is strength based. So we just design it for higher force, design it to have elastic behavior up to much higher force, and we assume that somehow this drift limit will be taken care of. Right? So this is what we are trying to do as a approximation for this drift control ideal. Right? What we are trying to do is we are trying to achieve desired performance by imposing higher force. Now this has been done, using importance factor in 2000 till 2016 version of the code, and in 2025 all that has been done is in place of importance factors ranging from 1 to 2, there have been different return periods have been specified. But essentially, all those return periods also do the same thing. They are just increasing the intensity of the load. So, for example, this 175-year return period may be this, occasional maybe 475-year return period, rare maybe 1000-year return period, very rare maybe 2500-year return period, so on. Right? So, technically, using importance factor versus using return period to define the excitation intensity, earthquake intensity, is really a cosmetic change. There is nothing in the 2025 version of the code that talks about damage control or the drift control. The design is still based on the old standard strength based design, followed by check on the serviceability drift limits. That's also nothing changes. Only change is instead of importance factor, you just mention the return period of the event computed through a very involved mathematical process. I'll come to that mathematical procedure in a while. Now, how do we come with these numbers? 175 here, 475 here, 975 here, 2475 here. So, world over, these two return periods are very common. Design basis, they call 475-year return period, and maximum considered earthquake is referred to as 2475-year return period. Now, this is an arbitrary uh, specification. There is no choice. There is no rational. Why should 475-year return period be the design basis return period? So this figure came 475 year and 2475, 475-year return period. This came in ATC 306, Applied Technology Council Report 306 in 1978. There was a committee constituted to come up with a comprehensive set of guidelines for earthquake resistant design, and then the committee drew some uh, kind of contours, what kind of ground motion should be used for design, So it was a consensus decision amongst the professionals, practitioners of the field. It so happened that at the same time, two gentlemen, uh, Algermison and Perkins from United States Geological Survey, they published their probabilistic seismic hazard map for the peak ground acceleration, horizontal peak ground acceleration in for the United States. And it so happened that what they plotted for 475-year return period, they aligned very closely with the recommendation of that committee, the professional engineers who were looking at this earthquake problem. And that is how 475-year return period came into practice. So it is essentially American practice. Now, just a little while back, I emphasized the difference in socio-economic conditions in America and the socio-economic conditions in India. So there is no reason why this 475-year return period should be used in India without any justification. There are cost implications involved, and the calculation itself is very uh, a different issue that I will come to, and very significant issue. Now, even in this 475-year return period, Alger Mason and Perkin, they used a particular way of computing it, and but bottom line is it was adopted as a standardization practice because every time committee cannot uh, be interested to work on some number. So if there is a formal way of arriving at similar kind of, I mean, which seems reasonable. So that is how 475-year return period was used. But somehow this 475-year as design basis has stuck all over the world except in Costa Rica. Costa Rica doesn't use this. And Costa Rica, by the way, sits right on the Pacific Ring of Fire between next to between Nicaragua and Panama. So a ring of fire, and still they do not use this 475-year, or they don't follow this recommendation blindly. And Costa Rica, the GDP per capita is about $30,000 US dollars per annum. So it is much smaller than America, but much larger than what we have. So now we come to the variation, I mean the comparison of the seismic zoning maps of 2016 and 2025 that we have. So the most obvious difference is increase in the seismic zone from 4 zones. We have now come to 5 zones, from ranging from zone 2 to zone 6. And just to compare the basic seismic coefficient that we use for design for normal structures, now the definition of normal structure has also changed. That's the fine print. While normal usage of a residential building was for buildings with occupancy of up to 200 in 2016, in 2025 version of the code, that has been limited to occupancy of only 100 residents. So 100 residents, what does that mean? About 4 or 5 storied building. If you go more than 100, the force levels increase by 20% more. Right? So this is for normal, so apple to apple comparison. So I'm just comparing these basic design coefficient to be multiplied by the seismic weight in the to calculate the design force base shear. So for the seismic zone 2 in 2016 it was 0.075, that is 1.5 is the load combination factor here. There is, which has changed to just 1 in 2025. So here it is 1.5 multiplied by Z by 2. So Z was specified in terms of MCE, DBE was just half of it. So that comes out to be 0.075 for zone 2. In 2025, again it is 0.075. Zone 3, 0.12. Here it is 0.125. Zone 4, it is 0.18. And here it is 0.233. Zone 5, it is 0.27. And in 2025, it becomes 0.33. And then zone 6, it goes to 0.5. Right? So, and then how this map has evolved. Now, this has been designed, worked out using probabilistic methods that is based on seismicity rate, and that is a uh, commendable job. It does take care of the active regions from less active regions, giving due importance to where large earthquakes are more likely to occur, and so on. While this was essentially derived from overlapping isoseismal maps of past large significant earthquakes in this region, and that is what contributed to these isolated uh, islands of, these are all mesoseismal areas of past earthquakes where maximum damage had happened, right? So statistically, they may not be as equally seismically active, but nevertheless, that was how it was worked out. So that this indeed is a major step, moving from isoseismal based, which is independent of the seismicity rate of the region, seismic activity in the region, to this range. But even here, I find these isolated pockets a little uh, uncomfortable. I don't really know whether these really follow the size. This is of course the Koina, so it is active region. But these regions, why do they have these isolated pockets of small pockets of zone 4 within a belt of 3, right? And similarly, this small pocket of 3 within this large tract of zone 2. So I don't have access to the data how this was done, but seems little unusual from the statistical point of view. So some notable difference, as I just mentioned, the partial factor in the load combination has changed from 1.4, 1.5 in 2016 code to 1.0 in 2025 code to partially offset the higher perception of seismic hazard. For the case of normal structures with importance factor 1, this brings parity in seismic loads in seismic zones 2 and 3 across the two regions. But the effective seismic design forces increase in the range of 23 to 85% for seismic zones 4 to 6. And if I increase the occupancy to 100 or beyond 100 up to 200, then the increase is 20% more. Now, Kutch region has been designated as zone 6. This region. I don't know why this had to be, such high design force level for Kutch region. This is one region which has experienced magnitude 7 plus earthquake in 2001 and not a single CPWD building damaged. I moved around with CPWD officials in the region, Bhuj region. We could not find any CPWD building which was under any kind of distress after that earthquake. They were immediately usable, fully, without any repair or anything needed. So they were immediately put to use after the earthquake. So when in view of this, when that building, those buildings, CPWD buildings, which were designed according to 1984 version of the code, they performed so well, why was there a need to increase the seismic design forces to such great level? 85% increase in the seismic forces here. Why? How is it that justified? And by doing this, all the buildings which have been designed according to 2016 version of the code are now deficient. How do we repair? I mean, do we really need to repair? How do we repair? And who pays for the repair costs, upgradation cost, and what is the rationale? What is the rationale for those imposing that demand? So different intensity of earthquake hazard is now specified in terms of return periods, but the performance specification is still in strength terms, as I mentioned. So all this return period business has done is replace importance factor with return period. That's just a cosmetic change from importance factor to return periods. Practically nothing in terms of performance based design. Absolutely nothing. Performance based design requires control of measure of the damage, measure of the drift, how drift is to be, what extent of drift is permissible for which return period or which particular event for different structures, configuration or use type. Right? There is no such. There is no such specification. Only what was done till 2016. Higher forces were used to design more important buildings. Just return those, replace those higher importance factors with higher return period intensities. That's all. Nothing actually changes on ground. So reading between the lines, seismic hazard is prescribed in terms of the ground motion parameters. So while we specify the ground motion design, when we talk about the design of this structure, what is of interest is the structural response to this ground motion. And distinction should be made between exceeding ground motion threshold and exceeding structural response threshold. Right? These two are distinct. I will try to explain, and that's why I will take a little small detour uh, to discuss the dynamic response of structures. How do they uh, depend on ground motion characteristics? So it is important to understand the ground motion characteristics to understand how structural response is influenced, and most importantly, not every high intensity ground shaking is hazardous for structures. Right? Please note this line. Not every high intensity ground shaking is hazardous for structures. So ground motion characterization, essentially any dynamic excitation requires three parameters. Three macro characteristics are required for specifying the load. One is, of course, the intensity. Second one, because it is dynamic loading, frequency content is also required because there is a problem of filtering. Right? Some frequencies more vulnerable, are more damaging, and some frequencies are less damaging to a particular structural type. And then the duration of the shaking, ground excitation. So if something is only lasts only for a very short time, it really structure doesn't respond. Right? So persistence of ground shaking is also important. So I will explain this particular uh, idea or this important characteristic in a short while. So these three macro characteristics are governed by the physical parameters of the earthquake process, that is the source mechanism, magnitude, distance, I mean whether it is strike slip fault, uh, thrust fault, whether it is subduction zone or tectonic, I mean plate margin or intraplate, so on. The magnitude, distance, site conditions, etc. All these factors combine to generate the motion at site. So just to give you an idea about earthquake ground motion, this is an accelerogram recorded at Gopeshwar during the March 29, 1999 Chamoli earthquake in Uttarakhand. So near field earthquake, that this Gopeshwar is less than 20 kilometers from the epicenter. So as you can see, these are the three components: longitudinal axis of this instrument, vertical component, and transverse axis of the instrument. As you can see, while the earthquake itself, the record is about 25 seconds long, the critical phase is only about 5 seconds. That's all. If structure survives these 4 or 5 seconds, that's all we need to worry about. The structure will survive others, right? And this is what we can ascertain. These are the ground acceleration traces. So we can measure what is the ground acceleration, peak ground acceleration, as you can see, about 0.38 g in this transverse component, and a very strong lurch here. So this is a near field event. It has all the characteristics of near field ground motion, strong pulse behavior, so on. Now, as I said, earthquakes come in different shapes and sizes. So this particular figure is very, very instructive. I mean, Professor Chopra has taken uh, great pain to plot all different several earthquake time histories, ground acceleration time histories on the same time scale and same y-axis. Right? So different earthquake events. El Centro 1940, then Chile 1985, Mexico City 1985. As you can see, there are different varieties of earthquakes, of differences in the duration, differences in the intensity, and so on. I bring your attention to this, I draw your attention to this particular event, Stone Canyon 1972 event. Right? The peak ground acceleration of this event is about 0.7 g. 0.7 g. And what was the magnitude of this earthquake? 4.7 magnitude recorded at 10 kilometers. And this is a very, very small event. This is just in one peak, and that's all. Nothing happens. This particular time history, if I evaluate any structural response, nothing is going to come out of it. Right? So this is not a damaging event at all, but still it contributes a huge peak ground acceleration to the database, and that corrupts the data, that distorts the data. When I take a statistical analysis, this will distort this particular data. Like this is going to distort the picture, and because we are only dealing with the maximum values, we don't really know whether that large value actually comes from a damaging earthquake. This earthquake here, although not anywhere close to 0.75 g, is much more damaging. Chile 1985 was very damaging earthquake. El Centro 1940, peak ground acceleration only about 0.34 g. This was very damaging earthquake. This is not really, nothing actually happened, right? And yet it will appear as a very large PGA in the database for statistical processing, because we only record this larger value, right, for statistical processing. We don't really take into account whether this value actually comes from damaging earthquake time history or not. So coming back to Gopeshwar, so this is the frequency distribution. What you saw earlier was a time domain description, how the waveform evolves in time. Now if I take it to Fourier domain, frequency domain, this is how the energy is distributed with respect to frequencies. And from here we can see that around 2 to 3 hertz, the structures with natural frequency between 2 to 3 hertz are going to have trouble here, because that is where the earthquake is feeding energy. So 2 to 3 hertz, right? Now, complementary part of any Fourier transform is the phase angles. Phase angles could be in principal values or in unwrapped phases. They have their own importance in signal processing, but not so much for hazard characterization, so I will let it pass. Now, if I bring the two together, time domain and frequency domain, this is what the time frequency plot of that transverse component of Gopeshwar ground motion is. As you can see, around 5 seconds, just before 5 seconds, we have the maximum intensity, maximum surge of about 2 to 3 hertz, maximum power, and then energy gets distributed over time and frequency. So it is in this particular time and frequency zone that structures are most vulnerable. So how does ground motion affect the structural response? So this is El Centro time history that you saw here. This is the same El Centro 1940 S00E ground motion component that you see here. And we consider the single degree freedom system oscillator of the 3 different periods. And how do these single degree freedom oscillator respond to this base acceleration? So this 0.5 second oscillator response is what you see here. So the relative response with respect to the base, ground. 1 second oscillator response is this time history, and 2 second oscillator response is this time history. As you can see, oscillator response is essentially filtering operation. So long period 2 second it allows low frequencies to pass through, and it suppresses the high frequencies. And short period allows high frequencies to pass through, and it suppresses the low frequencies. And if I pick up the maximum response here, so that, and I plot it here with respect to this time period on the x-axis and the maximum value on the y-axis, this is what we get as response spectrum. So maximum response for specific value of damping to the same common excitation. So this gives us the maximum response, and that's a very handy tool for dynamic analysis because it gives us a very quick way. I mean, I just estimate what is natural frequency or natural period, and I read what is going to be the maximum response of that structure to a given excitation, and then work it out to find out what is going to be the maximum force in the column or spins, because I just have to multiply it with the spin constant to get the maximum.